Welcome back to the Foundations of the Computational Economics. In video number 9, we're talking about a very exciting topic on algorithms and complexity. As you would remember, a few videos ago, we talked about different ways of calculating a polynomial. A naive approach would be to calculate the terms of the polynomial one by one, and then sum them together in the end. We could do better by trying to avoid recomputing powers of x. And let's see how that can be done. In this code here, I've written up a little function to calculate the polynomial, which is given by its coefficients, and a particular value. By default, it's 0. And as you can see here, we have two different algorithms to do it, a faster algorithm and a slower algorithm. Well, the slow algorithm basically cycles through the given coefficients, and for each of them, it takes x to the appropriate power, and then accumulates the result, the value of the polynomial in this variable rs, by adding up the coefficient multiplied with the power that it was just calculated. Unlike this approach, the faster algorithm does something slightly differently. Not only result is initialized at the first coefficient of the polynomial, and that's the one that corresponds to the constant. It doesn't have to be multiplied with x to the power of 0, which is kind of a waste of time in the previous implementation. But it also initializes the power of x to the value where we are calculating this polynomial, x, over here. Why is this done? Well, then we can arrange from the first element, so from the element indexed 1, which is the second element in the list, and accumulate the results similarly to before. But before going to the next coefficient and thus the next power of x, we can just multiply the variable xpw by x, and therefore we are also accumulating the powers of x. As you can see, similar to the result. As you can see in this second implementation, there is no power operator like here. And therefore, it is more efficient. Now, it would be nice to actually see that and see how these different algorithms compare. Let's do that. In order to run some runtime tests, we need to know how you would time the code in Python. And there are several ways, or there are several modules that allow you to time the run code, to time the running code in Python. There's a time module, there is timeit module, which we will be using today, and there are more, which is just more advanced. And then there are even more advanced profilers. There is a couple of standard ones, which would be very helpful in order to find where a bottleneck of a particular bigger program might be. And of course, if you have a large body of code to work with and you think it runs slow, then it's always a very good idea to run a profiler, see where where time is wasted, where would be the most efficient application of effort in order to speed up the whole code. Okay, we will be using the timeit today, and the way this is done is through what's called a magic command, starting with the @ sign. Or double @ sign. The difference is standard. One applies to the line and the other applies to the whole cell. And as you can see, we can give a bunch of options here. There's a good documentation here on the read the docs. You can see there are several options here that we may provide. the more important of them will be the number of repeats and the number of times the code is actually run. Where's that? That would be -n. You have to run the code several times, actually many times, to accurately measure the runtime, just because usually what we want to measure or what we might want to measure runs so fast that idiosyncratic processes on a computer may affect it quite a bit. But then we also want to repeat this run several times to calculate statistics on the on this runtimes, because again, due to the idiosyncratic influences from different other programs running on the computer in this particular time, you should treat the runtime as a random variable rather than a precise measurement. And so let's see how the calculator for the polynomials performs. As you can see here, we're timing the whole cell, and the statistics will be calculated from 100 independent runs, but each run will provide the runtime measured as an average of 1,000 runs in itself. The polynomial is quite large. It has powers up to 99. But all the coefficients are just ones. So let's run this. Oh, and I get an error. What's the error? Calc polynomial is not defined. It's probably that I forgot to run the code to define the function. So let me run this and go back and rerun. And here we are. So it's calculating now. I can see the processor starting to fire up, and there we are. So it takes about 55 microseconds plus almost a microsecond of a standard deviation on the 100 runs. Okay, let's try to do it the faster way. So here now we're giving the fast algorithm through the third input, or we're requiring. Oh, and that was much faster. Was it almost 3 times faster, in fact? So let me repeat the test just in case. Now it's, as you can see, choosing a correct algorithm is making quite a difference. Right, so what is an algorithm? When we say algorithm, we understand this as a sequence of commands that computer would run. It doesn't matter which language a particular algorithm is implemented in, although of course different languages have their different stronger and weaker sides. But the algorithms is an idea of a program more than an implementation, and organizing the calculation in a better way would probably work better in any computer language. What are the questions that we should keep in mind? Well, how much time does it take to run? Obviously, we don't want to wait for too long to get the results. But a lot of the times you can make things run faster if you use more memory. And so how much memory a particular algorithm is using is also very important. And you can measure the performance or complexity of the calculation in both in terms of time or in terms of space, where space means memory. What other resources may be limiting? Well, if you're running a large calculations on a distributed system, for example, where many computers are performing calculation on different parts of the problem, then it's important to think about communication, the speed with which the computers can exchange information. That could be a limiting factor. Other things to consider could also play a role in designing a sort of an efficiently performing computer code, efficiently performing calculation. The bottom line and the main idea that this lecture is focusing on is that smart algorithms is always a very important thing. It is in fact much more important than fast computer. If you employ an inefficient algorithm, then it may well be that no existing computer can deal with a problem, whereas by writing a more efficient algorithm, you can crack it right away. To support this last statement, here's a quote from Professor Martin Grutschel, who is a known expert in optimization. He's saying that in a benchmark production planning model would have taken 82 years to be solved in 1988, and only 13 years later, only about a minute. Well, that's a huge improvement of about 43 million, and only 1,000 times faster became the computers. The rest, the factor of roughly 33,000 was due to the algorithm improvements. All right, so let's look at several algorithms which are representatives from their corresponding classes of the algorithm complexities. The first one we're going to be looking at is called the parity of a number. So this is a very simple task. We just need to check whether a given number is even or odd. The idea here is that we'll look through several examples of algorithms from sort of easier to the more complicated to understand how the complexity classes are defined and how to think of complexity of computation in general, so that this equips you later to decide on the algorithm to solve a particular model in economics. So parity of the number just checks the whether a number is divisible by 2. This is done quite easily, but so if I run this, you can see that I'm importing a file called algorithm examples. This is a code file that you can run by clicking here, or in the normal notebook view. You will not miss it. This is just a large code that I'll go through the details of in the next several videos. But here we're just going to be using this code as is. So let's look what we're doing here. From that code, we're going to be just using the function called parity. Parity returns true or false depending on whether the number is divisible by 2 or not. In order to check how long it takes for these functions to work, I'm using the same time it command, or magic command, to return this time. I'm doing this five times here, and CK is taking values from a list which is created by the list comprehension, and here's the little formula that tells us how K should grow. On the output you can see that we've checked the parity or timed the checking of the parity of different inputs from 10 to 100,000. And it takes what? It takes about 200 nanoseconds everywhere. Well, do you think it's going to take the same amount of time for any different number? Let's see if we can maybe visualize these numbers a little bit better. We haven't looked at how to make plots yet, although I've started using plots sort of without telling you too much about how this is done. Visualization is going to be a topic of a different lecture. So let's just not think too much about this. I'm using the module called matplotlib, and there are some commands here that make this happen. And the plot is actually created down here in the end of the code. The important thing is that we're plotting n, x, and standard deviation, so the error bar plot will create some visual representation of the accuracy of these numbers. But the main thing is, what are we doing? So we are having a 50, and this is going to be the main loop, 50 runs of this code here. So first we are incrementing the value k, and the way it's done is the same way as in the previous slide. And then we are populating this pre-initialized lists where n records the size of the problem, and in this case the size is given by the number of bits that are required to represent a number k. We're calculating the parity of this number, and then we're saving the average runtime and the standard deviation in the runtime. Let's see what this produces. You can see that the code creates this, outputs this series of different times, and if you look at these numbers, you can see they're all pretty much around 200. And here's the plot. The runtime is on the vertical. Now I have to go to the standard view to be able to show you the plot really well. So here's the plot. The runtime is on the vertical axis, and this is the number of bits in the input argument. Well, what do you think? All the movements are within the more or less error bars of this plot. And like I said, this is just plus minus a standard deviation instead of, I don't know, 1.96 if that was a normal distribution. But even so, you can see that, it's very hard to track any sort of dependence or correlation from this data. It's pretty flat. What does it tell us? Well, it tells us that with the parity algorithm, no matter how big is the number that you're checking for parity, the runtime of this code is pretty much the same. Okay, let's go to the next example. Here the question is, let's find a minimum or maximum value from a list of numbers, of unsorted numbers. How do we do this? Well, sort of a standard and a very simple approach is just to go through the list of numbers and track the one that is the biggest or the smallest. Can we do better? Well, I can't think of any other way to find a maximum or a minimum that would not require checking every element of the list in the worst case. So if, like I said, the numbers are unsorted, maybe if they are not completely unsorted and we can use some additional information, maybe we can do something faster or better. But in general case, that seems to be the only way. So we're going to use the function from the module of examples for today, which is called maximum from list, and give it an argument x. Now x is a list of uniformly distributed values between 0 and 100, and the length of x is given by this size equals n. Now these functions, random, uniform, they come from another module which we will look at later, which is quite central actually in the computational works in economics, and that's called NumPy. But again, don't pay too much attention to these details yet. We'll look at them in a video too. So if I run this, here's my list of these uniformly distributed numbers, and the maximum there is 96.4585. Is this right? 96, yeah. Let's run it again, a different list and a different maximum. But yeah, it seems to work. Again, we'll look at this particular algorithm in the next video, in fact, and code it up. Let's try to collect some statistics on the runtime of this algorithm. The code is pretty much the same as before. The only difference is that on each iteration, we are creating a new list with a new length. The length is what increases, and the length doubles each time we run the code. Now, this length is actually recorded as a size of the problem. And we want to see how much longer it takes to solve this problem as this size increases, and graph the results. Well, it's going to take some time, as you can see. It's going to take some time. We're running 50 iterations of this main loop. And what the average time is a little bit under microseconds, and now came up to about 9 microseconds. And with the algorithm that has to visit all of the elements of the list, and remember, we are creating a bigger and bigger list every time on each iteration of this algorithm. Here's the graph of the runtime. Again, it's the runtime on the vertical axis and the number of elements in the list on the horizontal. What do we see here? I think this is a pretty clear linear relationship. There is some noise over here towards the longer lists, but I can imagine putting a line through all of this error bars, which are again plus and minus standard deviation. So I guess the conclusion here is that with this algorithm, if we have a big problem, and if the problem is twice bigger, then it would require twice longer to solve it, to find the maximum. Finally, let's look at the third example here. The third example is a game. Well, the algorithm that we will be looking at is called binary search, but the game is a game that you all probably know. Two players. One is picking a number between 1 and 100, and the other player is trying to find that number by asking questions. Is it below or above a particular guess? The first person can only say yes or no. The question I want to ask you really quick is, how many questions are required to locate the number, and what is the best sequence of these questions? Take some time to think about it. Okay, well, maybe you had the right idea, and the right idea is to break this interval of numbers from 1 to 100 to equal parts, or roughly equal parts, and continue doing that. Until you get down, sort of zoom in on the number which was chosen. So let's see how it's done, how it performs programmatically, and we will look at this particular algorithm in two videos down the line. But here we are interested in the runtime. So again, we're going to be looking at a particular size of the problem, and here the size is the length of the vector with numbers where something is chosen from. In the game, it's just 1 to 100, but here we are making it a little bit more difficult. This is a vector of random numbers between random integers, in fact, between 0 and 100 of a length n, where n is 10. And we are not allowing any of these numbers to repeat themselves. So replace equals false stands for that. Now, in this algorithm, we need a sorted list. So binary search works on sorted data. So we also sort these random numbers just to make sure they come in the right order. Although there can be gaps between some of these numbers. Now, this k0 is going to denote the one number that is chosen out of a list. And the binary search algorithm that gets to know the list and the value of the chosen number is going to be searching for it. And here's a successful run. Out of an array of these numbers, the number that was chosen, you can see it here, x of k naught was 5. And the index of this number, the algorithm is telling us is 0. That's the first number in the row, and that's correct. Let's run it again. Here's the set of numbers, which is sorted. The chosen one was 4th, 0, 1, 2, 3, 4. It's 55. And that's what the binary search was searching for, and it found the correct index for this number. You can run it many times, and each time you can see that the chosen number is the one which is found. Okay, nice. How much time does this algorithm take? And again, as before, we are more interested in how this runtime grows as we increase the size of the problem, rather than how much time it just takes to run once. And here we're going to be running 50 repetitions. The step function is a little bit different, so it's a linear function of the step. And we want to allocate a very long list of random integers, just to save time, not to spend time on that. Instead, what we will do, we will give to binary search a subset of this long list of integers, of sorted integers, a subset of them of the varying lengths, and this is done here. Now the value to be searched for is again a randomly chosen one from the list, from the correct list, right? From the correct subset of the values. Now here's an interesting point. We need to delay this algorithm to reliably measure its runtime, but that's a technical detail that I'll probably come back to when we actually code up this algorithm in one of the next videos. The rest of the code is pretty much the same. So let's run this one, and you can see it takes about 600 microseconds to run. Oh, I have to go back to the normal Jupyter Notebook screen to see the outputs. Well, we are running 10 runs of binary search, which is slowed down, and we are collecting 100 points before calculating the statistics for each size of the input. I guess it's almost done, but you can see that the runtime actually grows. So it was 600 microseconds, and now it's in milliseconds. Let's look at the output. And here's the graph. Runtime on the vertical and the number of elements in the list on the horizontal. Well, what do you think? To me, it looks very much like a logarithm function. And to check that, I'm actually plotting the second time here, and I'm just making the x scale to be a log scale. And by doing it this way, we would expect to see a linear function if the underlying was log. And as you can see here, yeah, we get pretty much a linear function. So this is a logarithm, which basically means that as you increase the size of the problem for this binary search algorithm, the runtime increases as a log. Why is it so? Well, the intuition is quite simple actually, and we'll go back to this when we code up the algorithm. But if you have a problem of size n, and this is the length of our list, and you're able to split it in sort of in halves, and then choose the half that is the one that you're actually interested in, and here imagine that let's think back about the game with the chosen number between 1 and 100. Imagine that the chosen number is this one. So by splitting the game in half, or roughly in half, and choosing this side as identifying this side as having the number that we're seeking, you can quite efficiently not pay any attention and spend any effort on exploring the other side. Now, with this side, remember the number was here. Now we can split it in half again and identify that the thought for number is in this part, and so forth until we arrive at the number in question. So, how much work is done? Well, the work is actually measured by how many questions you have to ask, right? How many levels this tree has. And you can see that as if we switch into two different branches every time, then the size of the length of the list grows down each time with a factor of 2. So essentially, we stop when n divided by 2 to the power of x, where x is the number of levels and n is the initial size of the problem, equals 1. And this is when we identified the chosen number. And so now that of course means that 2 equals 2 to the power of x taken logs. Log n over log 2 is our x. So given the size of the problem n, the algorithm complexity is proportional to log n, and that's the main result in the analysis of the complexity of the binary search algorithm. The formal way to talk about the log n is so-called big O notation. When we say that a function f of n is a big O of some other function g of n, all we mean is to say that g of n, it bounds our function in absolute terms, starting from some large value of n. And in other words, we're saying that when f of n is a big O of g of n, that means that f of n does not grow faster than g of n. And that becomes very, very useful. We should say that when we say it doesn't grow faster, we actually mean the worst case, right? The focus of the computational complexity theory is the worst case. It could be that sometimes, the algorithm may perform better if it's lucky, right? An average case is also sometimes interesting, but we really focus on the worst case, and therefore all of this comparison of the order of growth is not greater than. Right, so what classes do we have? Well, we have constant time, and that's the parity algorithm that we've discovered, right? The runtime in the parity algorithm does not depend on the size of the input, and this is a big O of 1. There is logarithmic time, big O of log n, and it says log with the base 2 here, but it doesn't really matter because, of course, you can convert the bases by multiplying with a constant. And according to definition, constants don't really matter, right? There is an arbitrary constant over here. Logarithmic time is the binary search. Now, linear time is the search for the maximum of a minimum in an array. There's also a quasi-linear search, which is the n log n order of growth. And if we go higher, then the quadratic, cubic, and so forth, polynomial time algorithms. And these are the last algorithms which are tractable, which are computable. Everything else, everything above that is said to be subject to the curse of dimensionality, and these are the algorithms that require exponential or even combinatorial time to be run. In this plot, you can see how algorithms sort of occupy the plane of problem input size and the runtime, and everything below red line is acceptable, is workable. But unfortunately, there are problems which are growing faster, the solutions to which are growing faster than the polynomial time. And sometimes we have to deal with these. Here's just a list of the examples we looked at and the classes they belong to. But what about the examples of the exponential runtime algorithms? Here's a simple example. This is a model of allocation of a discrete good in the economy. And imagine there's a welfare function that defines the utility of the allocation among n consumers, and a budget constraint which says that the sum of allocated portions should equal to a fixed amount of good that exists in the economy. Now, the important thing here is that it's only divisible in steps of lambda. How do we solve this problem, and how complicated is this? Well, let's see. Let's first denote capital M as the size of the step that this good can be measured in, and then define integers pi such that they sum up to this amount of good in terms of the unit lambda. Yeah, I should say that that M is not the size of the step. It's the amount of units of this good. So the welfare maximization problem is now equivalent to maximizing W with respect to the price to the vector of P's. Interestingly, the vector of Pi's to Pn is called a discrete composition of a number m, of an integer number m, into n parts. And this is an object that we can study and try to work with in order to solve this economic problem of the discrete good allocation. So the generator for these compositions we will look at in the next video, in one of the next videos. But let's see how hard the problem is. So first, there is a formula to calculate the total number of compositions, and the formula is combinatorial. It's m plus n minus 1 choose n minus 1. We will look at the derivation of this formula in that video as well. So imagine that n is 4, only 4 agents in the economy, and there's only 8 units of good. To calculate the number of combinations, we need this function from SciPy special, and that's another module that we import in here to be able to use the SciPy special comp function to calculate the number of compositions. And here we are just enumerating these compositions. By the way, the enumerate is a special command that goes through the list. Goes through a list of the compositions, but attaches basically an index to each of them, and the index is going to be stored in I. So let's run this. You can see that first of all, there's 165 compositions for 4 agents and 8 units. And here are the compositions. The very first one, index 0, is basically give everything, all 8 units, to the last agent. And then the algorithm generates this, different allocations of goods to the 4 agents. And it goes through actually all of them, all 164. Well, 165 if you include the index 0. Okay, how fast does this number grows? So if we imagine that we had 10 goods and still 4 agents. The number is 286 now. What about 5 agents and 10 goods? The number is 1001 now. And let me skip printing the compositions now. Now, if we go higher up, say there's 100 of the units of good. Here's the number. It's now in millions. And if we have more agents, I don't know, 15 agents, the number becomes very quickly. It becomes just astronomical. And this is the example of growth, which is quite common in these combinatorial problems. Well, however, let's try to measure the runtime of this composition generation algorithm, and we'll only do 10 runs with a fixed m, which is the fixed number of units of goods, and we will increase the size of the problem as one index, the n, by 1 at each step. So this is what we're doing here. And we're timing the composition generation algorithm. Now, it has to be called in a special way, and we'll cover why it is the case in the video on compositions. It has to be part of the for loop to properly work. And you can see here that we're only doing 10 repetitions to collect statistics, and we're running the algorithm just twice. Well, because it's quite expensive computation to run, and we still have to wait for it to continue and to finish, I believe. We're doing 10, 1, 2, 3, 4, 5, 6, so it's done 6 quite fast. Here's 7th, but then it may take some time. So instead of waiting for this, let's continue to the next slide and then come back and check what the runtime and the growth of the runtime is there. What are other important exponential algorithms? Well, it turns out that many generalized versions, n-by-n generalizations of the board games are exponential growth. Some very interesting economic problems, such as traveling salesman problem, is exponential. And now many of the problems in economics are actually subject to the curse of dimensionality, and these are the problems that we actually have to work with. It's not very easy. It's not very easy business. So what to do when you have to face a heavy computation with a problem that maybe doesn't have a polynomial solution? Well, always the first thing to keep in mind is to design a better solution algorithm. So, for many important economic problems, even though the fast solution doesn't seem to exist, it doesn't mean that it doesn't exist. Maybe there is still out there, and we have to find it. A common route is to analyze the special cases of a particular problem and rely on the structure of the model itself to try to speed up the computations. And this has been done very successfully in different classes of economic models. Now, we have to always think about how to speed up the code. So even if the problem is intractable in general, so the runtime grows too fast as the size of the problem increases, well, maybe we don't have to look at the very large problems, and we can still make contributions into economic research by considering a particular size of the problem, which we can still solve, even though it belongs to the intractable class. So here we have to think about the low-level languages and compilation to machine code. We'll talk about that later in the course. We always have to keep in mind that parallelization of the computation is something that can help. So employing a large computing cluster or just a large computer with many co-processors, it can be a way to go. Finally, bounding the problem to the space or subspace where it produces interesting, relevant economic results can be a way to keep it tractable. So we don't want to waste computations to the areas of the parameter space where things are not interesting or not realistic. Well, and the final point here is, of course, we always wait for the improvements in the computational technology itself. Okay, let's check back to the code here, and you can see it's still running. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, it's on the last iteration, and we should expect results soon. Let's talk a little bit about the P versus NP problem. So we said that the polynomial class, the algorithms with polynomial runtime is something that we think of as being sort of normal, tractable, doable. And there are many problems that belong to this class, meaning that they have solutions which run in polynomial time. But the theoretical study of the computational complexity actually talks about a whole family of classes of different problems. And here they're thinking about, problems in general, very, all problems that there can be. All the problems that can be solved in polynomial time. This is the class P. Interestingly, there are problems which are hard to solve but easy to check. So there is a class which is defined formally as non-deterministic polynomial time, and that means that you may be lucky, or you have to be lucky actually, to be able to arrive at the solution in the polynomial time. And you can think of this as being a hugely parallelized process. So non-deterministically, you're trying many different ways to solve the problem in the same time, and you arrive at the solution. So with one computer, that would require some sort of magic guess algorithm that guesses always right. And in real life, it could be actually an exponential solution algorithm. But the important thing is that it can be checked. The solution can be checked in polynomial time. Well, examples are, games of Sudoku, for example. A solved Sudoku is easy to check. And this is unlike chess, where a computer saying that a particular move is best in a particular position is very hard to check. Now, the class which is called NP hard is the class of all problems which are at least as complex as any as any NP problem, and so these are really hard problems, right? And finally, there is a class which is called NP complete, which is both NP and NP hard. So it's subclass of NP, which is as hard as all the rest of the NP problems. And here the interesting thing is that the NP complete class has the problems which are all linked to each other. And so if one of them is solved, essentially all of them will be solved very soon, or immediately rather. Oh, there's a typo here. So the typo should be not equal. And interestingly, it is still not clear, or it doesn't have a proof whether P is equal NP or not. And assuming that P is not the same as NP, here's the diagram of the classes of NP hard and NP complete being part of NP. Here are the easy problems. Here are the problems which are easy to check. Easy to check. And here are the problems which are all linked together. These are the hard problems which may be very hard to solve, including the exponential problems and even harder problems than that. The P equals NP is an unresolved problem that has a price of $1 million placed by the Clay Mathematics Institute. And if it is true, that means that a lot of the problems which we consider as being quite hard now could actually be workable. Unfortunately, the consensus is that it's probably not true. It's very hard to engineer luck and to devise an algorithm that will somehow magically choose the path to solution which is easy to check. Let's go back to the results here, and we have the graphs. You can see how the exponential time runtime looks, right? The number of elements in the composition the dimensionality of this problem grows just a little bit, and the runtime just skyrockets. It just goes through the roof. In order to see whether this is really an exponential growth, we can scale the vertical axis as a logarithmic scale. And here, a logarithmic growth, or exponential growth, would look like a straight line, right? A straight line of some slope. It doesn't really matter which slope, but it must be a straight line. And with this test here, what we actually have, we have a concave, right? A concave curve, which means that this runtime is not quite exponential. It's probably a little bit slower than exponential, which might be good news, but it still, grows very, very fast. Anyway, that's still a good example of the exponential growth. Okay, to conclude, here's the list of learning resources. If you're interested in the complexity further, there is, this is really a subject of computer science. But here in the computational economics, we also have to know about the complexity of the algorithm and of the algorithms, and try to use the algorithms which are more efficient. But if you're interested in the complexity in general, I would recommend this wonderful lecture by Eric Demain at MIT, which was given some years ago now, but still is very enjoyable. 50 minutes. And as I said, there are several resources of different levels of difficulty to continue thinking about the P versus NP and other problems in complexity. Okay, see you in the next video.